Sound waves are different than electromagnetic waves. They're longitudinal waves. So in other words, they travel the same direction that the medium travels. So if the medium is air, the air particles travel this way, the waves are going to travel the same direction. Waves travel the same direction as the medium. And they need matter. Sound waves, longitudinal waves need a medium to travel through. They need matter. They need something to travel through to vibrate. So if you set your alarm clock in space, and space is a vacuum, there's no medium, you're not going to hear the alarm clock go off. You don't hear sound. Nobody will hear. You don't hear anything. There's no sound. You scream in space, nobody hears you. Light waves are much, much faster than sound waves. So if we were to compare light waves and sound waves, light waves travel 300,000 kilometers per second, or 300 million meters per second. 300 million meters per second. Sound waves travel about 340 meters per second. So we're comparing 300 million meters, light waves, to 340 meters per sound. So much, much slower. And this is why, you know, if you in a lightning storm, you see the lightning, but you don't hear the thunder till later, because they happen at the same time, but it takes longer for that sound wave to travel. Light waves slow down in solid. So if light in a gas, like in air, travel much faster than in a solid or liquid, such as in the water. However, sound waves are the opposite. Sound waves actually travel faster in a solid or a liquid. They're slower traveling through the air and gas. Sound speeds up in a solid, because think of solids. These are the atoms in a solid. They're all packed together. And remember, sound waves are mechanical waves. They need and they're longitudinal. They need a medium to travel through. They need matter. They need matter to pass through. So they need these atoms to pass through. And if the atoms are closer together, like in a solid, they can vibrate easier. Because that's really what sound is. It's just a vibration of the atoms. Right? So since they're closer together, it's much easier. In a gas, these atoms are spread out more. So it takes a lot longer for them to vibrate. The intensity of a sound wave is really how loud the sound is, how much energy the sound wave has. And this is due to the amplitude. So the amplitude is the distance from the resting position to like the crest, or the resting position to a trough. So if you increase this distance in sound waves, increase the amplitude, you're increasing the intensity. So the sound is louder. It's a louder sound. The intensity of the sound increases as you get closer to the source of the sound. Obviously, this makes sense. If you hear an ambulance coming towards you, it gets louder as it gets closer. So if the ambulance is moving away from you, the intensity decreases as it moves away. So as you increase the distance between you and the sound source, you decrease the intensity of the sound. In other words, it's not as loud. And that is because the sound waves, since they have to travel a longer distance, oftentimes they can be absorbed by gases in the atmosphere. So intensity is the loudness of sound, and it's measured in decibels. Every 10 decibel increase, the energy increases by 100 times. And normal conversation is about 50 decibels. So 50 is about the normal conversation decibel range. The sound of an airplane taking off is about 150 decibels. Listen to a song and listening to the different tones The different tones you hear are really based on the different frequencies of the sound. With sound, the frequency is the number of vibrations per second. So different sounds you hear are really due to the difference in frequencies, or the difference in the number of vibrations per second. Sounds that have a higher frequency they're vibrating more per second. So higher pitch sounds, higher frequency, higher pitch, higher frequency, more vibrations per second. Lower pitch sounds, lower frequency. Lower frequency, longer wavelengths. Higher pitch sounds, higher frequency, shorter wavelengths. So if you think of pitch, it has to do with the frequency of the sound. Higher pitch, higher frequency, more vibrations per second, and that means you're going to have shorter wavelengths. So up here, here we have longer wavelengths, lower pitch, lower frequency. So our perception of sound wave frequency, how many vibrations per second, is really called pitch. So if you think of higher pitch, higher frequency, shorter wavelengths, lower pitch, lower frequency, longer wavelengths. And that's just perception of the frequency of the sound waves. How many vibrations are there per second? Sound waves are examples of analog signals. And analog signals vary continuously. They can vary their wavelength, frequency. There's lots of ranges, possibilities, lots of different pitches of sound. Digital waves are measured in pulses, kind of like on or off. And that's when we think of digital, think of computer systems, zeros and ones, on or off. There's no in between. It's like black or white. Digital, black or white. Analog, there's a lot of gray area. So when we're looking at our technology we use now, it's mostly gone digital. And we're going to just examine the difference between analog and digital waves. The advantages of analog, what's the advantages of digital waves.